Hello students, today we are going to learn AC generator. This is the next topic of electromagnetic induction. In 12th state book, the entire chapter is given in one chapter, one topic, okay. But in CBSE book, this portion is divided in two parts. I mean, in electromagnetic induction, there are two chapters. One contains the inductions, mutual inductance, and then the transformer, etc. And then there is the AC generator. So today we are going to see the brief idea of AC generator. AC means what? Alternating current generator. Sometimes it is also called as AC dynamo. And in our day-to-day life, we use two types of sources, voltage sources, I want to say. And sometimes we discuss in our while solving numericals about the DC voltage and AC voltage. So today, first we will see what is the difference between the AC voltage and DC voltage. See, the DC voltage for the mobiles and for some gadgets we use the DC voltage supply, whereas for our home appliances like for CFO light, for LED light, for fan, for running the geysers and washing machines, we use the AC supply. Okay, so AC and DC. As an example, DC means direct. Okay, it looks like this. If I plot the graph of time versus voltage, you will find the voltage is constant and it doesn't change its direction. Okay, magnitude is constant, and we know the source of DC voltage. Very first source which was invented. You know, this is photo like electrolytic cell. This is one of the source of DC voltage, okay, and we use battery for the DC voltage, and AC also converted into DC. That is a different part. We have seen in the semiconductor topic that AC can be converted into DC and we can use for our home appliances which require the DC. So this is all about the DC voltage. DC voltage is constant. It is unidirectional. Right here, it is constant. It is constant. Then unidirectional. Unidirectional means the voltage is constant. Say 12 volt, 4 volt. For your mobile, you use 4.5 volt. For the LEDs, sometimes you use 12 volt, sometimes you use 3 volt, different type of LED. And then it is unidirectional. The direction of this source does not change. So this is all about the DC voltage. And sources. Very first is, you know, you might have learned this in your 9-10 syllabus. The cell, okay, electrolytic cell, there is S2SO4 and then zinc and copper plate. When you insert, then there is chemical reaction, and chemical reaction is converted into the electrical energy. And chemical energy is converted into the electrical energy. When you insert, when you deep this electrode inside, okay, EMF is generated. There is ionization, lot of things, and then there is the EMF over here. Okay, and this way the cell, whatever cell we use in our day-to-day life was on this principle only. And while talking about the AC, so in our home appliances, to run the home appliances, I want to say the geysers and the washing machine, the fan and tube lights and your dryers and so many things, we use the AC voltage. AC means what? Alternating. AC means alternating. This particular voltage AC is bidirectional, or you can say it is like this, alternating. If you look at this waveform, you can see that the amplitude of this waveform is varying. The amplitude of this waveform is varying, and also the direction of this waveform is varying. Suppose I put it here time and this side as a voltage, then you can see over here you will find the amplitude is less and it is gradually increasing. The amplitude is gradually increasing, and also the direction. Now look at the this peak. It is going up, again coming down and meeting to the zero. Then again coming down in negative axis. This is positive axis. This is positive cap, and this is negative cycle. Okay. So you will find here the direction of this AC waveform is continuously changing. Also the magnitude. So in AC, the direction and the magnitude both changes continuously. So, you know, what is the source of this AC voltage? What is the source of this AC voltage? Where from we get the AC voltage for our appliances? for our offices, for our home purposes, where from we get this AC voltage. So basically there are 4-5 sources of AC voltage, AC generators. Very firstly, like thermal power station, then hydraulic power station, then atomic power station. Okay, yeah, thermal power station, hydraulic power station, atomic power station. Okay, and there could be few more. Okay, and how then AC is generated in thermal power station? In thermal power station, the coal is used to boil the water, and from the steam, okay, the turbines is rotated. Okay, turbines like this. Okay. When the heat force is applied in this rotates. This particular fan will rotate, and this way the turbine will rotate. Then in hydraulic also. Okay, in hydraulic means water. So suppose I draw here one fan. Suppose this is a fan. I put it like this. Suppose the water is falling on this fan. What will happen? This will rotate. Okay, and here also this particular thing is rotated with the help of the steam. In atomic power station, the atomic energy or atomic heat, atomic heat in fusion and fission, there is a lot of heat is generated in the reaction. So that particular heat is used to boil the water, and once the water will boil, the steam is used to rotate the turbines. Okay, now here in all the three cases I am using one important thing, that is what? That is the turbine rotating something. And why I am detailing about all the things, because what I am going to detail about the AC generator, there is something, unless we rotate it, we cannot generate the AC generator. In short, we have to rotate something, okay, and unless we rotate that coil or that thing, we cannot generate the AC voltage. So first understand in thermal power station and for hydraulic and also in atomic. And when you go out some places, maybe at the hill station, you find the windmills like this. Okay, like this. My drawing is very poor, I think. You might have seen the windmills. Okay, this windmills, it rotates and AC is generated. Now in all the four cases, something is getting rotated, okay, to generate the AC generator. So now we'll start how AC is generated. First, we understand that in AC generator we generate something. Not only this, in when you ride a bicycle, okay, here the wheel is rotated, and somewhere here we fit the dynamo. When the wheel rotates, okay, this dynamo will get attached to this rotating ring, and it also rotates. This dynamo also rotates, and once the dynamo starts rotating, you'll find the light glows, the headlight of the cycle. Okay, the headlight of the cycle glows when the dynamo rotates. So sometimes, therefore, the AC generator is also called as dynamo generator or dynamo AC generators. Now we'll start the topic AC generator. Now we have seen in last few lectures, when we rotate a coil, whenever we rotate a coil in the magnetic field, the flux gets induced. In the coil, and there is the induced EMF or induced current. Okay, we have been learning this in so many days, that whenever we rotate the coil in the magnetic field, in the paramagnetic field, the flux get associated with the coil, and there is induced EMF. So that means to generate the voltage, we have to have the magnetic field. So here I will draw the strong magnetic field. Suppose this is a horseshoe Now this is the north pole and this is the south pole of the magnet. Okay. Generally, electromagnet is used to create the strong magnetic field. Okay. Normal magnets are not enough to generate the voltage, so we use a strong electromagnet to generate the magnetic field. Now we know that the magnetic field line will go like this direction. Okay. Yeah, from north to south, and when I will put a coil in this, suppose I put a coil, I will change the color. So A, B, C, D. Okay. So arrangement is something like this. So this is north pole, this is south pole. These are the strong magnets. Generally, electromagnetic magnets are used to create the magnetic field, and this is the uniform magnetic field. And when I will rotate this particular coil, what will happen? The voltage will get induced in this coil. Okay. What I will connect one fan over here. Okay. So you will understand this better way. Okay. Suppose this is a fan or something. Okay, which will rotate. That means we'll have to rotate this. We'll have to rotate this particular coil to generate the voltage. Now we know this. Now at present, if you look at this diagram, this coil is parallel with the magnetic field. This coil is parallel with the magnetic field. So no flux is getting involved in this. No flux is involved in this. That means what? There won't be any EMF. So EMF will be equal to what? 0. Now when I will rotate this coil, what will happen? When I rotate this coil, then you will find that the flux get involved in this. Flux will get involved. Okay, and because of that flux, there will be induced current in this. There will be induced current in this coil. Because of what? Because of the flux. As I rotate it, okay, the flux, more and more flux will get involved. When this coil becomes perpendicular to the magnetic field, becomes perpendicular to the magnetic field, the flux, the maximum flux will get involved, will get associated with the coil, and the EMF will be maximum. Again this mark is not related. So the induced current will be maximum when this coil is perpendicular with the magnetic field. That means what? Now there is one interesting phenomena which happens here by the Fleming's right hand rule. Okay, so this is field. Okay, this is a field and this is a force. Okay, this finger points toward the field, and this is the direction of the force. Then the direction of the current will be like this. This middle finger will show the direction of current. That means if I rotate the coil like this, the current will flow in this direction. Whereas while rotating the coil from that side, so this current direction will change. Okay, so that means first the current will rotate this way. Okay, and in second turn, direction will change. It will become like this. That means direction of the current will continuously change after 1/2 cycle. See, in DC, okay, when you apply the voltage, suppose I put it like this, okay, this is a DC source, okay, and you know the direction of current will be from positive to negative, so it is positive and negative. So current will flow like this. And electron direction will be in this direction. Electron will move in this direction. Whereas in AC, what you will observe in AC is denoted by this symbol. For first half, the direction of current will be like this. Okay, and in second half, okay, the direction of current will change and it will be in this direction. This one DC. In DC source, this is positive terminal of the battery, this is negative terminal of the battery, and we know that because of this potential difference, the electron will move from negative to positive, okay, continuously, and there will be flow of current from positive to negative. This is in case of DC. Whereas in case of AC means alternating. So there is alternately the direction of current changes. In AC, the direction of current alternately changes. So initially in first half cycle, the current will flow from positive to negative. Okay, and in second half, it will flow from it will change the direction and then it will flow from positive to negative this way. Okay, so it will be like direction will change continuously. Direction will change continuously. Okay, therefore the AC is denoted like this. AC is denoted like this. Now we know that when we rotate this field, when we rotate the coil in the magnetic field, the flux will be linked. Now this particular thing, this particular coil is called as armature. This coil is called as armature or rotator. Okay, it is a coil which is mounted on the soft iron core. Okay, thin copper wire winding is mounted on the soft iron core. Okay, and these are the magnet which is made from the electromagnet. Okay, now we know that once the coil start rotating, okay, there will be generation of current in this, and to obtain this current, we'll have to have some arrangement which is called as commutator. Here there will be separate arrangement of brushes and rings. And here I will connect the galvanometer. I can connect galvanometer. Okay, like this. Okay, so when this coil will rotate, okay, you can't just connect the coil directly to this, because once you connect the coil directly, what will happen? It will move fast and it will get break. So we use the brushes system. Brushes system is what? Suppose this is the coil. This is one side of the coil, and if you're rotating, I can just put my brushes like this. So this particular thing will be always get connected with this rotating terminal of the coil. There are two terminals of the coil. There will be two brushes which is used to keep the contact close continuously. Because in case I connect this directly, what will happen? This will rotate and the contact will get break, so you won't get the AC supply. Now I am using the galvanometer. The purpose of this galvanometer will show in first half cycle it will show the reading one side, okay, and in another half cycle it will show the negative reading. Means what? Initially the galvanometer will deflect, okay, one side, and it will show the positive half cycle, and in another half cycle it will show the negative half cycle. Half cycle. So initially when you rotate, at present the coil is parallel with the field, okay, once the coil start rotating for half rotation, what will happen? The positive EMF will get induced, it will go to peak and it will again come down, and in next half cycle the direction of the current will change, and it will move in the negative direction. Okay, so this way the AC will be generated in the coil and will have the AC supply. And for the high amplitude or high magnitude of the AC, we'll have to use the bigger magnet system, or bigger magnetic field, or bigger electromagnet, and the bigger coil. Okay, and there is one more important thing, that is we have to rotate, and to rotate this particular thing, we use the that is thermal or hydraulic or that atomic steams. All things are used to rotate this. If there is no thermal power station, then you will have to rotate with the hand. If you rotate with the hand, then you will have the AC supply. But to have the permanent arrangement, we use windmill. Okay. So when windmill rotates, that means it rotates this coil. When windmill rotates, it rotates this coil. When steams hit to this fan, it will make that fan rotate. Okay. Then in case of hydraulic also, high power water will fall on the fan blade, on this fan blade, and this fan will start rotating. So in all cases, there has to be something to rotate this particular coil. Once the coil start rotating, you will have the AC supply, and this particular supply we use for our household purpose. It's very simple. Now we'll derive some equation about this AC generator. Now we know when flux link with the coil, voltage the current get induced. Okay, so flux is what? Flux equal to magnetic field into area, and cos theta. Okay, and as there is number of turns, I'll write n here. Okay, now we know this, when we rotate this, then it is a rotational motion, so the omega is the angular velocity equal to theta upon t. So theta equal to omega t. So this phi will be n BA cos omega t. So flux will be phi equal to n BA cos omega t. Now we know that the formula for induced EMF, that is E equal to minus d phi by dt. So suppose I put the value of phi here, what will happen? So minus NBA, no, I have to write like this, minus d, phi value is NBA cos, what happened to my handwriting? Cos omega t, okay, upon dt. Now these are constant, the number of turns are constant, the magnetic field is constant, and area of the coil also constant. So I will separate that NBA and then d cos omega t upon dt. Now you all are good in mathematics, so the derivative of cos omega t is sin theta. Okay, so minus NBA sin omega t and then omega. Okay, so but omega equal to what? Omega equal to 2 pi f. Okay, omega equal to 2 pi f. So there will be now this 2 pi f omega is equal to 2 pi f and BA sin omega t. Okay. Now the one thing, this important factor in this particular equation is sin omega. Okay, and you know the value of sin omega goes on continuously changing from this way. The sin value of omega is goes on changing alternately. So when the theta is 90, when theta is 90, it is 1. When theta is 30, it is half. Okay, like this, the value of theta goes changing. So maximum value of theta will be, maximum value of this E will be when sin WT is 90. So E max, right here, E max or E naught equal to 2 pi f NBA. Okay, 2 pi f NBA, because sin omega t is maximum, so E max equal to 2 pi f NBA. Okay, so if I put this E naught, if I replace the 2 pi f NBA with E naught, then the equation will be E equal to E naught sin omega t. So this is the equation for induced EMF in AC generator. If I divide this with the resistance, okay, we know that B equal to or E equal to I R. Okay, so I will be what? E upon R. Okay, so if I divide this with R, we'll have the, if I divide this with the R, then E will be E naught sin omega t upon R. So I will be I naught sin omega t. So this will be the equation for the current, induced current. Okay. I will brief this particular topic again, student. Today we are learning AC generator. AC generator is the topic of electromagnetic induction, and in this we are learning how the AC is generated. So to generate the AC, we will have to rotate the coil in the magnetic field. To rotate the coil in the magnetic field, we use the different modalities like in thermal power station, in hydraulic power station, in windmills, and in atomic energy station. There is the turbines, and turbines are rotated, and when turbines are rotated, this particular coil rotates. When this coil rotates in the magnetic field, what happens? For half cycle, when the coil rotates half turn, okay, the current moves in one direction, and when the coil rotates in another half cycle, the direction of current changes, and because of this changing direction, the current we obtain is sinusoidal. The current we obtain is sinusoidal. There is positive cycle and there is negative cycle, and in the arrangement, this is magnet from strong magnet, and then the coil is called as armature, which rotates continuously, and there is commutator. To commute means what? Commute means to transfer the commute to go from one place to another place. So electron goes from this coil. Electron goes from this winding cable to the circuit or to the power, to the place where we are going to use the power. Okay. So there is a home like this. So the supply. So the supply will go from this place to this home purpose, and they can use it. So when the coil rotates in the magnetic field, okay, AC is generated. And to derive the equation, how we have derived this equation, we have first seen the phi. Phi means what? Phi means magnetic field, and that the area, how much area it cuts. So that is N is number of turn, B is the magnetic field, A is the area of the coil. N is number of turn, B is magnetic field, A is the area of the coil, and cos theta. Okay. Now we know that omega, the angular velocity equal to theta upon t. Okay, that means theta equal to omega t. So I have replaced this theta with omega t. Okay. Now we know the induced EMF equation, that is E equal to minus d phi by dt. Okay. So I have replaced this theta. I replaced this theta with what? With this particular thing, NBA cos omega t. Okay. So I have taken the derivative of this. While taking derivative, I have separated this constant number of turns, magnetic field, and area. These are the constant terms. So we have taken it out, and we have just taken the derivative of d cos omega t. So it is E equal to plus NBA sin omega t, and there is omega separate. Okay. So omega t is omega. So equal to 2 pi f NBA sin omega t. So this particular 2 pi f NBA. So this induced EMF will be maximum when sin omega t is 1. So considering sin omega t as 1, so E max will be 2 pi f NBA. Okay. And so E naught, that is maximum EMF equal to E naught equal to 2 pi f NBA. So when I replace this this 2 pi f NBA with E naught. So E equal to E naught sin omega t. So this is equation for induced EMF. Now talking about the induced current, I will have to divide this particular EMF by resistance. We know V equal to IR. So I equal to V by R. So here V is E. So if I divide this particular equation with the resistance, so E naught sin omega t is divided by R. So I have got the I equal to I naught sin omega t. That is the induced current. That is the equation of induced current. I hope students you must have understood this topic, and please go through the derivations once, twice, and enough for today. Next time, next lecture. Thank you.